Hello fans of GeoGebra. We have a new application that we haven't seen before, and that is the transformation of strain. The transformation of strain. So the problem is this. It's a elementary shape, but fairly complicated story to tell here. So we have an initially square solid, 1 meter on each side. And you see points A, B, C, and D defining the initially square solid. Then what happens is points A and B are displaced down 1 millimeter. Points A and B are displaced down 1 millimeter, and points B and C are displaced to the right 2.5 millimeters. So I inflated the deformation, or I exaggerated the deformation here. But we won't do that in the subsequent GeoGebra file. I just want you to clearly see it. And then the question is, well, there's a series of questions. Let's describe the displacement at any point on the structure. In the U direction, which is parallel to X, let's describe the V displacement, or the Y, in the Y direction at any point on the structure. Let's determine the strains in the original coordinate system, and you can call this gamma or epsilon, it doesn't matter. And then the kicker, let's get it on the alternate axis, and there's nothing magic about this axis, it's just a 4-3 slope, so that's given. That X prime axis is given. Okay? So how did we do this? Well, you could certainly do this by hand, or you could do it in a different kind of program like MathCAD here. But I did it in GeoGebra, of course. So let's walk through what I did rather quickly, and then in a subsequent video I will maybe describe all of the steps in a little more detail. The first thing I did was I drew the quad, which is really easy here, 0, 1, 1, 1, 1, 0, and the origin is D, which is at 0, 0. So you could see it here. So I'm calling this the original shape. Then I put in a number and I called it Shift X and Shift Y, and remember that was the shift in the X is, in this example here, 2.5 millimeters. It's exaggerated in this picture to the right, and the shift downward in the Y direction is 1 millimeter. So I put those in as 0025 and minus 001. The next thing I did was I drew the new rectangle, and you could hardly see it here until you really zoom in, and then, okay, now I see it, there it is. So here, for instance, B, you could see B has shifted 2.5 millimeters to the right and 1 millimeter down. So I'm going to hide the original one, and I will hide the original quad, and I'll just show you the distorted quad. Okay? So the nice thing about doing this at full scale is that you could just zoom in and see these things, right? I put in the axes here. There's nothing magic about that. I just drew a line. I called it the slope established point. So let's see if I could find that. It's at 4.3. It's way out here. Here it is. And then I just drew a line through my slope. Remember, we said it was a 4-3 slope. Okay, so we have the new x prime axis, you could see it here, and the new y prime axis here. Maybe I'll hide those for clarity right now. The next thing I did was I said, okay, what is the displacement of each point, each critical point here, A and A and C, excuse me, because I will assume a linear variation throughout the solid, a linear variation of displacements. There is nothing that says it is a linear variation, but let's start with simplicity. So I will assume a linear variation as we move through the solid. So all I really need is the x and y displacements of A and the x and y displacements of C. And they're really simple. The x displacement of A is the x value of AP minus the x value of A, which is 0. The y displacement of A is simply the y of A prime minus the y of A. And similarly for the C's, x and the y. Okay, nothing magic there. The next thing is slightly tricky here. Slightly tricky. So what I did was this. I programmed this equation, which is a linear variation as we swing from one axis to the other axis. So we're going to start at one point and go to the other point. And I am saying u is a function of x and y. This is one of the big changes in a mechanics type approach, that you have the displacement being a function of two spatial coordinates. And the same with v. V is a function of two spatial coordinates. But notice v is dependent on how c shifts and how a shifts. But once again, c is on the x-axis and a is on the y-axis. So I come up with this fairly nice function here. So you might want to just write this down here, and then I'll walk through it more slowly in a more detailed video. The next thing that I need is the actual strains. So the strain in the x direction is the movement of point C in the x direction divided by the original length in the x direction, and the strain in the y direction is the movement of point A in the y direction divided by the original length in the y direction. So how did I do that in GeoGebra? So I said epsilon x is the displacement cx divided by dx. So what I'm looking at here is the displacement cx divided by this original length. And remember, I just said what the displacement of cx is. It's cp, c prime, minus c. So you could slow this down if it's a little fast, but I want to zip through it because I want you to see the overall picture. So the strain in the x direction is the displacement of the point C in the x direction divided by the original length. And of course the y is analogous. It's the displacement of the y point divided by the original length in the y, and I'm calling that dy. And then the gamma is the movement of in the u direction divided by y. So that's the two angles of the racking or the distortion of the element. Du dy plus dv dx. So you take the opposite one here. The axial strains use u and x or v and y, but the shear strains use u and y and v and x. Not hard. That's not hard. So gamma xy happens to be 0 in this problem, which is not a big deal. So, but we could make this, we could use this script for anything. The next thing that we do is we program the clunky transformation equations. And I will do this with Moore's circle of strain later, but a lot of times students feel like they need these equations, but I actually prefer the Moore circle. But here are the equations. They're standard equations. We derived them in class. The direction cosines use the lowercase letter n x prime x, n x prime y. So n x prime x is the cosine going from the x prime axis to the x-axis. So that is not tricky. Here it is. That's theta. Happens to be 36.9 degrees. And then, and I just measured that here in GeoGebra. And then similarly, I will need the ny prime x and y prime y. But I just did a shortcut in here. I said ny prime x from y prime all the way to x. Let me repeat that. Y prime all the way to x is simply the theta plus 90 degrees. Theta plus 90 degrees. That's kind of a shortcut. And then our strain in the new coordinate system for racking or distortion or shear is this formula. And I did all of these in GeoGebra. So but before we get to that, I want you to see the u's because the u is really sweet. The u is, and you might have to stop the video here and take a peek at this a little bit. So what I said was, and this is the hardest part of the whole thing. I said in the u direction, in the x direction, the u variable is what it is at c as a function of x, and what it is horizontally at A as a function of Y. That is a thing of beauty. And I didn't come up with this. Somebody else came up with this. That is important. The U distribution or the field within the entire solid is assumed to be a linear variation, ladies and gentlemen, going from C to A, and I can check every point in between, but I only have B, but I could put it for any point on the solid. And why is this super important? Because we as engineers put strain gauges on solids, and we have the strain at some point, or the displacement at some point. And we interpolate what is happening in between all of the other points, ladies and gentlemen. You're not going to put a strain gauge on every point. And, you know, in the 1950s and 60s, they tried to do that with speckle photography and all that stuff. And you could do that with a computer, but this is a linear variation here. And let me show you the V, because this is the hardest part. The variation of V is analogous to what I just said for the variation of U. The variation of V is how much is C moving in the Y direction, and then I swing all the way over here, how much is A moving in the Y direction. That's really, really cool, I think, here. You can check now. I could check, for instance, B prime. I could check B prime. So what I did was I did B prime check because I know what B prime is. It's the given displacement of B, but I can check it with my properties here. And look at this. This is pretty slick here. So I said B prime check is the original B plus the U function at 1, 1 and the V function at 1, 1. And of course, B prime check completely matches B prime. Ladies and gentlemen, if C prime check doesn't work, you screwed up because C and A are the things that you fit the function the linear function. So let's just make a quick reality check here. So C prime check is C plus my U distribution at 1, 0 and my V distribution at 1, 0. And CP check works out, and similarly AP check works out. So I really like that. That's the hardest part. Then it's almost over. Epsilon x prime is the standard equation that I just gave you, the standard transformation equation. I'm not using Mohr circle here. And I can pop that in as simply as a little function here, epsilon y prime, no problem, and gamma x prime y prime. So hopefully you are impressed with the power of putting this fairly complicated idea on the children's program GeoGebra. It's a thing of beauty.